Thanks for the invitation. It's very pleased to have an opportunity here and talk about something I've been working during the past few years. And there are also some at the end of the talk point out some observations that we have quite recently. And so here I'm going to talk about scattering amplitudes. Of massless particles. And just to set up the context, I'm considering a particular quantum field theory on the Minkowski background. And but I just consider a generic space-time dimensions. I don't restrict it to any particular number. And the thing that I would like to introduce to you today is that for any scattering amplitude of massless particles, we can have express it in terms of a certain integral formulation expression of some matter with some specified integrand, which is alternative to the summation of Feynman diagrams. Now, let me first motivate this a little bit. So why would we like to consider this? So in general, as you learn from the first quantum field theory course, whenever we compute some this kind of object, the thing that we usually do is to sum over Feynman diagrams. But very often, if we really do so, actually we are wasting most of our much of our time, and because of the fact that the Feynman diagrams by itself contains a lot of redundancy. There are redundancies coming from the field redefinition, and also in particular if we consider gauge fields and say perturbative gravity, then there are also a lot of gauge redundancy. Once we choose a gauge fixing, each Feynman diagram itself is not gauge invariant, but we know that in the end, after we get the whole amplitude, it has to be a gauge invariant object. So there's a tons of redundancies in the computation, which doesn't really enter into the final answer. So there better be a way to make this manifest and make the computation efficient. And a second motivation is that there's a lot of interest in understanding the interaction of gravitons, even in the perturbative regime, and just to understand what's the general structure of this kind of object in the perturbative theory. But as you know, if we just expand the Einstein-Hilbert Lagrangian, we get tons of interaction terms at every multiplicity order. So the thing is proved to be quite complicated. We just deal with Feynman diagrams. And also due to this reason, for quite a long time, people don't really know what the general structure for any multiplicity until in recent years. First, let me give you one example of how things might be simplified. So even if we just consider scattering of gluons, already at 6 points, it's to do it with Feynman diagrams is very impractical. Even if we get to the final answer and express it generically in terms of momentum polarization tensor, polarization vector, the final answer could pile up into several pages. But then there's a remarkable observation in the 1986 due to Park-Taylor that there's a particular configuration of the helicity if we restrict to 4 dimensions. So usually when we study this gluon amplitude, since it has color structure, a nice way to organize the amplitude is first to group it, to expand it in terms of the color structure. And here in particular, we don't want to, a nice thing to use is not the structure constant, but in terms of the group generators. So if I use alpha 1 to denote the corresponding ordering of particles and consider n gluons, then the whole amplitude can be organized into a summation over an ordering, a summation over all possible orderings modulo the cyclic ones. And then for each this structure, we associate with a factor which only depends on the kinematics. And then we also denote it by a given planar ordering, the corresponding planar ordering, alpha. And so each time you can just study this object which only depends on kinematics, which we call the partial amplitude. And so the observation is that in 4 dimensions, we can try to express the momentum in terms of a two-spinner representation, which is basically you dot the momenta by the Pauli matrices. And then since this guy is we are considering gluons, it is massless, and that means the determinant has to vanish. So this splits into two spinors, a holomorphic one and an anholomorphic one. And then if we further say introduce a notation of for the invariant product of 2 spinors of the same chirality. Then it turns out that for a particular helicity sector, which we call MHV, basically it means that we are considering a partial amplitude of gluons where we only specify 2 of the particles to be of negative helicity while others to be positive. Let me use the canonical ordering. Then the result turns out to be quite simple. We have some factor which dictates which of the particles has negative helicity, and then the remaining thing is a very symmetric, cyclic symmetric and simple combination in the denominator. So before we introduce this clever parametrization for the kinematics and land on expression, just by doing Feynman diagrams, there's completely no clue why we should have landed on this simple final result. So back in those times, it's a sort of magic. And actually, over the 30 years, this has inspired a lot of developments in the research of the general structure of scattering amplitude. Now, whenever a remarkable simple result comes into being, it has to indicate that there are some underlying reasons that guarantees the final answer is simple. And so usually when this happens, we would like to think to try to think whether there are some kind of formal formulation that makes this trivialized. And the story that we have been learning once and once again is that whenever we can make a non-trivial property trivial, then usually we get some bonus because it helps us to discover more things. So one example that perhaps has been advertised a lot is that by studying the amplitudes in 4D maximal super Young mills, we get some nice geometric picture of the scattering amplitude. And more recently, there's some proposal of the amplitude hedron. Oh, sorry, amplitude hedron, where it's basically, it claims that any amplitude in this theory is a volume of a certain polytope called the amplitude hedron in some certain space. And so
that statement is for planar amplitudes?
Yes, the original proposal is for planar, but it's not exactly the amplitude, but rather the integrand. But this holds for any loop. And they have the hope that in that picture you may have some unified view of the whole amplitude, including any loops.
Any loops, but still in the planar limit?
Still in the planar. But recently there are some discussion extending this to non-planar limit. This is still work in progress, and people are discovering new things. Yeah. But here I'm just providing an example of how that by thinking really hard about these simple results, we may discover some new structures about the amplitude. Okay, and today what I would like to introduce is yet another direction of viewing these things. So let me start by reviewing a little bit what kind of non-trivial properties that the gluon's amplitudes satisfy in any dimensions. For the time being, we still just focus on gluons. So first of all, perhaps obviously, point one, that this gluon amplitude, this planar ones have to be cyclic invariant. This is something that you can already see from Farnham diagrams, not hard, and also under reflection, you might pick up a sign. Good. This is something that we can immediately perceive. But then there are some other identities that relates different the planar amplitude with different orderings. Firstly, there's a Yuan decoupling identity, which basically states that you can sum over the position of one particular particle over the insertions of the rest. You pick up one to be special and insert it in every possible position, and the summation should be 0. Roughly, this tells you that if you imagine this particle to be the photon, then it has to be decoupled from the remaining SUN group. And so the summation should be just 0. And there's actually a generalization to these relations, which is a little bit non-trivial, which is called twice-square relation. Here, we start from a particular ordering, but we take up 2 labels to be special, and then we consider some certain ordering, which then we denote as alpha and beta for the remaining guys in the whole planar ordering. And then this amplitude is actually, it has an expression as a summation over the other guys, where you specify, in each term you specify some ordering where 1 and n sit in the 2 ends, and you have some gamma, and this gamma belongs to the shuffle of alpha and beta transpose. But here, what this shuffle really means doesn't quite matter. It's just some expression that I would like to point out. After doing this, then when we look at this amplitude, actually we can specify n minus 2 factorial independent guys out of this whole summation. And so in real practice, when you try to compute the whole amplitude, you don't have to compute everything. You can choose some n minus 2 factorial of them, and then determine the others in terms of this relation. But actually, this is not the thing, the minimum thing that we can reach. There's a fourth relation, which is non-trivial and actually only discovered in the 2008 due to Bern Carrasco and Johansen. So in this relation, we specify some particular label n, say, and then we sum over another label, which let me call a from 1 to n minus 1. This time I'm putting a Mandelstam variable of these two particles, which is basically just the square of the summation of the two corresponding momenta. And then we take out another label b, which starts from a and sum up to n minus 1. And in this term, we put a corresponding matrix, corresponding planar amplitude, which has the ordering 1 up to b, then inserting a between b and b plus 1, and then up to n. Sorry. Sorry, the signature insert should be n, then up to n minus 1. This identity is quite non-trivial, as you can include some coefficients depending on the kinematics. So these are the relations that any gluon amplitude should be satisfied in any dimensions. Some of them are relatively obvious, and for example, for these two groups, roughly by looking at the Feynman diagrams that should contribute to the planar amplitude, you can immediately see that why this identity should hold. For example, for this one, it basically tells you that if you consider a bunch of n minus 1 gluons, and then when you consider the others, you insert in every possible place. But then, particularly for every left, you can insert either here or here, but they differ by a sign and the pixel. Of course, there are some complications due to contact terms, but in the end, everything works out. But these guys are relatively non-trivial, and so following this logic, we would like to see whether there are some ways with which we represent the amplitude so that all of them get trivialized. In doing this, perhaps we may find something very interesting about the general structure of the amplitude in a given theory. In this case, I mean the scattering of the gluons. And this is what I'm going to review to you step by step. So at the starting point, let us just play some game. So, sorry.
I'm a little confused by your statement of number 4, because it looks like the sum over b in it vanishes by the U1 type.
But here, pay attention. The starting point is different. Yeah. So as a group grows, the terms here gets reduced and reduced. Good. So let's do this. Let us temporarily forget that we are considering some amplitudes, not even the gluons. But just think about these A's as some kind of functions that we can design, whatever functions it is. Let me denote this function as some C. That depends on the same on some planar ordering as well, in order to mimic the story here. Let me propose a particular function for this. So let me define C as 1 over a bunch of vectors, which I denote as sigma first start with 1, 2. So this sigma, whenever I write sigma AB, I mean a sigma A minus sigma B. And I'm considering a set of variables, complex variables, of sigma 1 up to sigma n. Okay? And then this function I would like to propose as 1 over sigma 1, 2, sigma 2, 3, up to sigma 1 n 1, the cyclic sum, cyclic product. This is something that you might already have seen in in a computation, say, of open string, for example. Actually, later on, I'll draw some connection between them. But temporarily, this is just some proposal. An arbitrary nice function that you can write down. So immediately, we can see that these two are satisfied. And it's also now hard to check that the point 2 and point 3 are also satisfied just algebraically for any values of the sigma that you can design. So all these are completely solved. But then there's this 4 left. Now, if we try to play the same game using this function for the fourth relation, what we discover is that now we need to actually impose some constraint on the sigma variables. So first of all, if we study this combination, what it tells us is that after we plug in the C object, this becomes a C of one less labels. The label n is gone, but we have the same object C of a smaller size. And then it's multiplied by 1 over sigma n1 minus 1 over sigma na. Now there's something interesting because these guys are completely independent of the label A. So it becomes an overall factor which can be followed in front. So this doesn't quite matter. This is also an overall factor. And then its corresponding coefficient is just the summing over of these Mendel-Stem variables, which turns out to vanish due to momentum conservation. So this is also gone. And then by requiring that this relation to hold, we get a non-trivial constraint on the sigma variables, which is basically summing the label A from 1 to n minus 1. Then in each term we have S of na over sigma na. This has to equal 0. But this is just one relation by picking up a special label, which turns out to be n. And so in general, if we want the whole set of ECJ relations to hold, what it means that we need to think about this object. Let me define them as F, labeled by A, which has similar structure. We sum over all labels B that is different from A, and S AB over sigma AB. And then we need to impose that this FA should equal 0 for every A. Now, this is a set of equations which we name as the scattering equations. So far, this is just a game. We find some nice object which is simple enough, and by just imposing this constraint, as long as we find some solutions for the sigma, then the function satisfies all these constraints. So,
these are valid for any loop, or they are
these are all the tree level.
so
That's tree level.
so if you want to factor loop, these relations are not true.
No, a loop is not. It doesn't hold. Right. Right. Okay. So far everything is just a game, but we would like to see whether this can be really used in the actual practical construction of the amplitude. So what's the idea? But before that, let us try to think about what are really these variables that we're thinking about by looking at the properties of these equations. So I said that these variables at the starting point, I'm just considering some n copies of the complex space, C to the n. Now, if we have a little bit more study of this f functions, we actually find out that, first of all, these FAs are covariant under an SL2C transformation, where we transform each sigma variable to some sigma alpha times sigma plus beta gamma over gamma sigma plus delta, where these coefficients are complex in general and satisfy this relation. And under this transformation, each of the f's has to transform to itself but multiplied by a corresponding gamma sigma a plus delta to the power of 2. So as long as this equals 0 after transformation, this we have the same set of functions. And so that means for these variables, there's actually a redundancy if we think about it as being constrained by these functions. And due to this SL2C structure, the natural object that we can attach to these variables is that we are thinking about some a Riemann sphere, where we use this variable, inhomogeneous variables, to dictate the locations of the given puncture from 1 labeled up to n. And so, by doing this, we can think about that we are trying to mimic a scattering process by an underlying Riemann sphere, where each incoming particle are inserted on a certain puncture. This is some picture. It's not the worldsheet that we are thinking about in neural string theory. It's just something, or the auxiliary object that we can attach to these functions. Now, that means that effectively we have n-3 variables. So we should have to worry whether these functions are over-constraining, but actually it's not. So at the second point, algebraically, as long as the momentum conservation is satisfied and every particle is on shell, we can find 3 linear combinations where we put the sigma a to some power times the corresponding fa, and summing from 1 to n. This has to algebraically equal to 0 when n equals 0 or 1 or 2. And so the number of independent equations are also of n-3. And so what these equations tell us is that by imposing these equations, we are really carving out a zero-dimensional algebraic set in the modular space of n-punctured Riemann sphere. So this is a picture that emerges from this set of constraints. And in general, since it's n-dimensional, it's nothing but a collection, a set of discrete points labeled by a particular solution. And actually one can do the counting, and it turns out that generically the cardinality of this set is fixed to be n-3 factorial. So this is the number of the solutions to these equations for generic data. This is something that we can be perceived just from this constraint. So now we have a better understanding. We have this picture of an auxiliary space associated to a given set of kinematics for any scattering process. And so a natural thing to do is that whether we can find a way to represent the thing that we want to compute using this auxiliary object. So since we have this n-3 points of the solution to these equations, a natural thing to do is to think about some certain function. Let me denote it as I. It can depend on the kinematics again, but it can also depend on the auxiliary variable that we use. And then what we need to do is nothing but to evaluate the sigma variables on each of the solutions. Let me denote them by a label I, which I refer to as the I solution, where this I runs from 1 to n minus 3 factorial. And so we can think about some arbitrary function, evaluate them on the sets constrained by the equations, and then sum them over. And since these are all the solutions to these functions, it's guaranteed that as long as this is the starting point is a rational function of all these guys, then in the end we should get some rational function of the kinematics data, which has a possibility to be the actual amplitude at tree level. There are several ways that we can think about this expression. But to make things nicer, let me further divide it into two parts. And in one part, I'm using the same notation again. But then in the denominator, let me explicitly put out the Jacobian determinant, where we take the derivative of these functions over the corresponding variables and compute the determinant. So when we look at this expression, there are several ways that we can think about. One thing is that this might look like some kind of result obtained from a certain localization procedure. Perhaps we can start from some integral, and then there's a parameter that we can deform there, and then in the end the whole integral is localized onto a saddle point, which leads to this answer. And actually, if you have some familiarity with some old literature, this set of equations are actually dictating the saddle point of a string amplitude in the so-called Gross-Manner limit. In other words, this is a kind of high energy limit of a string amplitude and with fixed angle. In that limit, so usually when you consider the string amplitude, in particular, there is a Covariance factor, which comes with a power like this. And then in the higher energy, these are dominated by the saddle points. And if you write up the corresponding equation leading to the saddle point, those are nothing but these guys. However, the field theory amplitude naturally is obtained from the low energy limit instead of the high energy limit. So this, if one thinks in this way, at least it cannot naively work unless there are some non-trivial things happens. So this is one direction. Another way that we can think about this is that we are really considering some counter integration in the moduli space. So just to make this look more invariant, instead of considering explicit summation, we can consider some counter integral in the modular space where we introduce all these variables. And then they are further localized on the equations. And then we insert this remaining function, which here we call the integrand in this formula. Of course, here one should be careful because the variables and the constraints are redundant due to the thing that we have discussed before. And so here one should actually need to divide by an invariant volume of the SL2C. And also in writing out this constraint, we should mod out 3 of them and to compensate by a small Jacobian in order to make the whole thing computation invariant. And the way to understand this delta function is really that we are inserting 1 over s. But then for the counter, we are just specifying that we are winding around some t, and -3 torus dictated by that the value of these functions are a small circle around these solutions. So this is a general prescription that we would like to use. And for convenience later on, let me call this whole part as a measure and denote it by d mu. This is something that is universal for any scattering process as long as we consider just massless particles. For whatever process in whatever theory, if there's such a representation for the amplitude, this has to be the same. What differs is the function that we specify in the integrand. And so instead of discussing why this has a possibility to be the correct expression for a given amplitude, meaning that it respects the locality and unitarity, correct factorization, I'm not going to discuss that explicitly, but in the end, I'll just provide various examples to convince you that this really works. So we can actually start from something very, very simple. But in doing that, the only thing that we have to be careful is that since we have the redundancy of this induced by this SL2C transformation, but we also know that this Riemann sphere is some auxiliary object that we introduce. But in the end, the whole answer, in order to be an actual amplitude, it shouldn't depend on anything how we fix this redundancy. And so there's actually a constraint on the form of the function that we can put here. Mainly, we need this guy to behave also covariantly. Under any such transformations, what we require is that this integrand should also transform into itself times a bunch of factors, where it's again sum over all labels, and for each guy we put a gamma times sigma a plus delta 4 times. This is the only constraint that we need to pay attention in order to write something down so that the whole object is well defined. Now, already there's a very natural candidate that we have at hand, which is this factor. And in analogy with the formula I wrote down before, let me call this particular factor. Just to remind you of the cyclic structure of that simple object. Now, if you look at how this thing transforms, it actually already transformed covariantly, but with a power 2 instead of power 4. And so at the starting point, we can already try to think about an object where we put two copies of the same function. But since they are independent, we can put two arbitrary planar orderings specifying each other. And let me name this object as n, depending on two orderings. Due to this restriction of time, I'll not perform an explicit computation. This is actually just to solve algebraic equations and do this very simple thing. I'll just summarize what the result this is. Actually, the result is very, very simple, apart from the fact that to solve the equations looks very complicated, because this is in general a complicated system of several variables, and in general we would expect that even if we put in rational data, the solution could be non-rational and even complex. But it turns out the final answer is very simple. The answer is nothing but a summation over cubic scalar diagrams that are consistent with both planar orderings and beta. Let me illustrate what I mean by consistent. So, say, for example, if we have a given tree bi-cube diagram of 4 points. By consistent, I mean if we put this external legs onto the plane, respecting the ordering, whether the tree can be embedded that, fully embedded in that. And so by writing out this tree, it can be embedded into 2 orderings. One is 1, 2, 3, 4, and as another, you can switch one of any of them. So say 1, 2, 4, 3. But for example, you cannot embed this diagram into an ordering of 1, 3, 2, 4, because here you need the leg to cross each other. So this is not allowed. And so, in general, as a very simple example, if we think about some m of depending on ordering 1, 2, 3, 4, and 1, 2, 4, 3, this will single out a single bi-cube diagram, because we can first of all put a planar ordering from this, and then we basically use the other ordering to link them, and then immediately we can recognize that the only thing that can be put here are this single diagram. This holds more generally. For example, let me give you another example to see how this works. You can consider some at 5 points, 1, 2, 3, 4, 5, and specify another ordering to be 1, 2, 3, 5, 4. One ordering is 1, 2, 3, 4, 5. And for another ordering, we can again write out another loop, which runs from 1 to 2, 2 to 3, 3 to 5, to 4 to 1. And then we see that we allow this vertex. And then here we can either put the diagram of this channel, or alternatively a diagram of this channel. And so in the end, this object equals the summation of 2 diagrams, which looks like this. But apart from this, there's nothing else that is allowed. And actually, we can doing this mapping inversely. So in general, we can as well, starting from some specified trivalent diagrams, as complicated as you wish, it is always possible to find 2 orderings which filters out only this single diagram. This is always true, though I will not tell you the general procedure of how to algorithm of how to do the mapping. But this is something that you can do in principle, and also it's not hard to see that the corresponding integration formula is actually highly redundant. There are tons of integrand that you can put here, which basically lead to the same answer. Now, what we learn from this fact is that we can do this reverse engineering very generically. In general, we can just start by considering some amplitude in a theory where we can compute the amplitude using Feynman diagrams. Of course, everything should be massless. And your starting point is a bunch of Feynman diagrams. And for each diagram, let me also specify the numerator and denominator, label them by an I, running from all the Feynman diagrams. Now, in general, you could think about there are some contact terms of higher multiplicity, but it doesn't matter because you can always put some manual stem variables upstairs and downstairs simultaneously to resolve this into trivalent guys again. And so, in general, I could think about this object as being just the corresponding traveling scalar diagram. And so we can always write this into a certain expression and put in the numerators and address it with a certain integrand that does the job to produce the denominators. And since this part is universal, as I commented before, we can pull this integration outside of the sum. And regard this as the whole integrand for our amplitude. So by doing this, we have seen that just by studying this very simple object, we immediately know that basically for any massless scattering among massless particles, we can always write out some expression using this technique. And due to that dictionary, the things here are like just a trivial translation, and it doesn't really do anything remarkable. And in particular, in general, this looks very ugly. But what is really magical is that for many amplitudes that people are actually interested in, there's a way to greatly simplify this whole integrand, so that first of all it has a very simple and complex structure, and also it reveals some non-trivial structure of the scattering amplitude in a given theory in general. And to provide an example, now let's go back to the gluon scattering again. And let's see how the hope that we had previously for trivializing these relations can be achieved in this way. And so we have this measure which is general, and as we had hoped before, that we want to use this object. And so if say we are considering a planar object, a planar amplitude of a planar ordering, we put the same ordering in this factor. And then since this only covers half of the power, we need some other things, some other object. But what we can immediately say is that as long as this remaining object that we insert in the formula is fully permutation invariant among with respect to the labels, then the only thing that depends on the ordering is nothing but the C. And since this is built upon the support of the scattering equations, all the relations that I wrote before immediately get trivialized. And so what is this remaining object? It turns out to be, again, something very compact, and it has a universal expression for whatever multiplicity you consider for the scattering. So since we are considering scattering of gluons, there should be some dependence on the polarization vectors entering here. Generically, this object is expressed in terms of a function of a certain matrix that I call psi. This psi is 2n by 2n antisymmetric matrix with a block structure. Then we divide it into 4 blocks and name them as A, B, C, and minus C transpose. And the labels here are running from 1 up to n, and then 1 up to n again, corresponding to the particles. Here in the first block of labels, I'm feeding in the corresponding momenta. So here, for each element labeled by two particle labels, the element is the corresponding momental stem over sigma A minus sigma B. And when the two labels are the same, you just put 0. So zeros in the diagonal. The structure in the B is similar. So for each B of AB, we have the corresponding, but now this time we put in the polarization vectors when the two labels are different, and 0 when they are the same. So roughly it's like for the first columns in each entry we are fitting in the corresponding momenta, but then in the second block of labels we are fitting in the corresponding polarizations. And so the structure here looks, for the C matrix, looks like that we are using the in one part we are inserting the polarization, and in another part we are inserting the momenta. The only to be consistent here, let me not use the Mendel's terms, but instead we use a contraction of two momenta. But here the little bit complication is that for the diagonals of the C, we have to do something different. Instead, we need to put a minus of the summation of all labels different from A, if A and B are the same. And then we basically sum over the extent A contract with any momentum divided by the corresponding sigmas. This is the general structure of this matrix. The way to design this is that we need to recover two linear, to make the matrix to have corank 2 on the support of the scattering equations. And in the end, we actually need to define a sort of reduced version of this due to the redundancy. And the way to define this is that we pick up two labels, say I and J, and we are removing the corresponding rows and columns in the first block. And so this reduced function is defined by computing the function of a matrix where we delete these two rows and columns compensated by a prefactor in order to make the whole object to be invariant under permutation of the labels. This is the object, and by inserting this function in the formula, this reproduce the amplitude for gluons at tree level. So this is one of the examples that you can that we have that describes any scattering among pure gluons. And this provides the evidence that how this framework can be useful in formulating the tree level amplitude. But then, as I have mentioned at the start, that for quite a long time, there's also a hope that we can get a better understanding of the interactions of gravitons in the perturbative regime. But in general, it is very hard to get even just to work out a nice formula for that. Back a long time ago, almost the only practical way that people knows about how to even just to perform the calculation of graviton amplitude is by what is called the KLT relation. And here I actually need to add a negative, meaning that this is a field theory KLT amplitude. Because later on I'll point out that this relation actually originally comes from the integration of strings. But just to come back to the story, what this relation tells is that in general, if you want to consider some graviton amplitude, you can express it as a linear summation of product of two gluon amplitudes. So we need two copies of gluons. Here let me name them Young nodes. It's the same. But it's not a simple product. Actually, we need to specify a certain ordering. Again, let me denote it as 1, 0, n minus 1, n. So here, in a particular example of this kind of relations, I'm fixing 3 labels and try to commute the rest. Correspondingly, in another copy, we are using some other ordering where we also fix 3 of them. And now we need to insert some kind of function, which let me denote as S0, depending on the two orderings rho and sigma. Divided in this way, sigma rho. And then we need to sum over the rho and the sigma, belonging to the permutation group of n minus 3. So this is the general structure of what we call the field theory KLT relation. The detailed structure of this object here is not very important for our current discussion. The only thing that I would like to point out is that for a given specific ordering, the corresponding entry is nothing but a product of Mendel-Stan variables, and this is a homogeneous expression. Okay, and so this is what people for a long time know about how to do the GR before they have some more fancy techniques like doing on-shell recursions or something else. But still, it's very hard to find a closed expression for any amplitude in GR as what we have here, or even say something similar to the Taylor amplitude, which has this simple expression for the gluons. In general, there's nothing as simple as this for gravitons. However, once we have this tool, we can actually find a very simple expression for the gravitons, which reveals a remarkably simple relation with the gluon amplitude. And that also provides a generalization of what people normally call the field theory KLT relation. But before that, let me point out that here, since we are considering a summation of a permutation of n-3 labels, so it's in general like we are considering each of the amplitude as n-3 factorial size vector of Yang-Mills amplitude. And this number happens, if you still remember, this matches the number of solutions that we get from the scattering equations. This provides some hint, or from another point of view, you can think about that the equations actually kind of suggest why we have this number here. But to be more explicit, we can start by thinking in terms of this. So just recall the object that I wrote down before, this n function, which is expressed as the integration, where you, in the integral, you put 2C object. Okay. Also, I pointed out that this is nothing but a summation over n-3 factorial solutions, where on each we evaluate them on the solutions. And also, we need to divide by a Jacobian coming from solving the system. Here, further, let me split this into 2 parts and evaluate each of them on the corresponding solution, which I label using this. Say, if I give a name to this matrix, which let me call V of labeled by the ordering and this solution. And this by another matrix whose entry are labeled by another ordering and this solution. Now we can think about this object as being some big matrix as long as we pick out some certain n minus 3 factorial different ordering of them, arbitrary things that you can think about. This whole thing as a big matrix is exactly a matrix product. Now, right, and furthermore, using this identity, we can determine its inverse, which is V transpose inverse times V inverse. Now we can try to let's call this by another name. Let's call it K naught. And then we can think about some combination where we take the same Yang-Mills amplitude, but with some more general ordering, but still of the sign n minus 3 factorial. We sandwich it by K naught, depending on two orderings, and another A labeled by the ordering B, at beta, and sum over alpha and beta. And since if we write this again out into a similar expansion, we're doing nothing but to replace one of the C's by this permutation invariant object function. And what turns out to be is that one copy of such structure in this amplitude cancels one of the inverse, and another structure coming from another amplitude cancels another inverse. And so in the end, what we get is another summing over solution, but with the two objects look like this. Each of them evaluate on the I solution. And we sum over all the solutions. But again, this can be turned into an integral, where for the integrand, we just put two copies of the stuff. And furthermore, if we identify these two bases of the orderings as the one that I choose here, it turns out that this K naught is exactly identical to this S naught. And so in this way, we know that the gravity amplitude emits this simple expression. And from this point of view, the relation between the two is nothing more complicated than replacing one of the factor by another copy of the function, where by which you basically insert another copy of the polarization vector to compose a polarization tensor. And this is one of the remarkable outcomes that we receive by playing with this representation. And it actually tells us even more, because originally this guy is something that we learned from the spin theory. But now we see that there's actually a very general, we can generalize this to a more generic context, not even just to replace its orderings by some other kind of basis. But we can even think about KLT relations between theories which, without knowing all this, there's completely no clue why they should have the relation. Just to give you one example of what I was commenting on, what this discussion implies is that suppose we start by consider some two copies of theories. Let me denote them by by theory T1 and theory T2. And in each, suppose we have some either color structure or flavor structure, so that we can consider planar of amplitude due to similar decompositions. And further, if both of them can be expressed in terms of one copy of the particular factor, and then in another thing, in the remaining part, we can insert some permutation invariant object depending on the theory. The two slides can be different. Then there should exist some KLT relation, which let me generically denote them as a product by KLT. Following the same prescription, then this should lead to some representation where we just insert these two integrand. And this should compute something else that we might expect in a third theory. So this guy should be some integrand between a third theory, which hopefully is permutation invariant. As one example, we can think about this I of T1 to be the function again of this psi matrix. But in another, we can actually replace, put it as a square of another function. But now, this time, this is not a function of the whole thing, but a function of this, just this part. We pick up this matrix A. Since it is again antisymmetric, we can compute some function of it. But then in order to make the transformation correct, we need to put two copies. Actually, it turns out that for this theory, this T2, once we impose this, what it computes are the amplitude in the Yuan nonlinear single model. This is some scalar effective theory where you can do the decomposition of the flavor structure and then acquire some planar amplitude. And then you do the KLT product of this one with gluons. And then for the third theory, as a result of this product, it turns out to be the amplitude in Born infield. So this is one of the examples that this application of the KLT relation can work as one of its natural consequence. And yeah, so and this is the main thing, main application that I would like to discuss in this introduction of the scattering equations and its use. In the remaining part of the talk, I would like to switch focus a little bit and turn to discuss an observation on the string amplitude. One of the motivations leading to this observation is that, as I pointed out before, when we look at the form of the scattering equations, it looks like some set of equations determining the saddle point of a string scattering. And so it's very natural to wonder whether this kind of formulation really has some rigorous connection with the ordinary string amplitude, even though the underlying Riemann sphere does not acquire the picture of a real string wave sheet, at least not in the naive way. The observation is actually quite simple. So just to remind you again, in the original story, when people discovered this KLT relation, I think it's back in 1986. What they first realized is not any relation about the field theory amplitudes, but rather the relation between amplitudes in closed strings and amplitudes in open strings. There's a corresponding similar KLT decomposition. So in general, the picture is like this. Roughly speaking, when you consider a closed string formula, you are integrating over the plane for each unfixed puncture of some correlation function that you compute from the vertex correlations. And then in natural computation, when you want to determine the whole result, you are actually viewing, say, for each variable, you are viewing this as a two-dimensional counter in C2. So along the real axis, if you consider the two things to be independent and counterclockwise. And then you do some non-trivial counter deformation, and in the end, you fold each of them into some real counter integration, like as if you are integrating along the boundary of a disk. And then, due to the counter deformation, there are some non-trivial pieces picked up in the deformation that remains outside the open string amplitude. And in general, the structure of this kernel looks like a product of sine functions. And inside each sine function, we get some of alpha prime times some non-standard variables. And then to land on the field theory relation, it's nothing to take the low energy limit. And correspondingly, the open string reduced to the Yang-Mills guy if we just consider the math-based external space. And then immediately this string theory kernel reduced to the corresponding field theory one, just by the simple fact that the sine functions are approximated by the corresponding argument. Now, the comment that I would like to make here for the observation is that the validity of this identity actually depends on how we look at this expression. What I mean by this is that, say, if we let's imagine, suppose, let's consider two universes that are linked by some wormhole. And suppose I let two scientists, one scientist, one sit in one universe, another sit in two. And you ask them, both of them, to compute some open string amplitude by their own, and send the result into hexagon compute. In principle, you cannot ask them to coordinate and fix this common convention. Then let's imagine that if we ask the particle physicist to sit in one universe, and then let a general relativist to sit in the other universe. And then there's actually something magical happens, because one of them tends to use the mostly minor signature. However, the other would like to use the mostly positive kind of structure. So you seem to get something nonsense in the computation. Okay, you might think that, that this is something completely nonsensical, and we should express something that is crazy. However, the actual story turns out to be not true. And to make the thing more precise, let me even restrict to a very special case. Let's just consider the type 2 string. Then here the claim turns out to be very simple. Suppose we insist that they are doing this query things surely this cannot be a closed-ring amplitude. However, what it turns out to produce are exactly the corresponding type 2 supergravity. This is something completely not obvious from this product structure.
So where is the low energy limit?
There's no low energy limit. So this is something that I would like to emphasize. Firstly, due to what this result tells you is that all the massive poles are just gone. Nothing there. And also further, the remaining interaction are that are the interaction that respond in this supergravity. And further, at the second point, this identity holds for generic alpha prime. For any alpha prime values, you get this identity. Or in other sense, after you do this, the dependence on the alpha prime on the left-hand side is nothing but a trivial overall factor to some power in order to compensate the mass dimensionality. But this doesn't really do anything non-trivial on this part. So this is not in any limit. You study it for any alpha prime, and it works. Just to give you a little sense of how this might be true, let's even look at some pole examples at 4 points. I will not use an example of an actual amplitude, but use something that is quite similar to what you may encounter in an amplitude calculation. So let's play with this integration. Just 4 points, so we can fix 3 of them, and left with 1 puncture. And we write out the Cobaniusian factor. And by this S and T, I mean the corresponding channel in the Euro convention. And I'm setting, for convenience, I'm setting a particular value for alpha prime. And for the remaining integrand, I'm using this structure. Okay. If we turn this into an expression of a KLT form, then what we have is this. So on one side, we have something that looks like an open string, which is just a product of rational function of the gamma functions. On the other side, we have another thing that mimics the open string. And in the kernel, we have a single sign function depending on I t. Now, after doing this multiplication, of course there are many massive poles and there are single poles. But now if we follow this procedure, we take one of them, then the difference in the convention asks us to switch the sign in front of each Mandelstam variable. Then at 4 points, we immediately see that, first of all, this gamma of u cancels gamma of u. So there's completely no pole at the u channel. And then further, this gamma of minus s cancels this gamma of 1 over s. But then we are left with 1 over s pole. And then for the remaining thing, this t, we have 2 gammas and 1 sign. And it's easy to see that the combination of these 2 gamma functions have single poles in every integer. But then there's a corresponding 0 here, so they completely cancels away. And so in the end, we're left with a single massless pole. So this is an intuitive example of how this cancellation of massive poles can happen at 4 points. However, this is something very special to 4 points where you don't really have a genuine matrix multiplication. You can try to do some similar check at 5 points. However, at 5 points, you expect this to be a product of size 2 on each part. Immediately, in this case, when you want to verify the cancellation of message poles, it requires non-trivial combination between different terms, and immediately it's no longer obvious. There's a certain incomplete proof of this relation as long as we assume a certain property, a certain structure of the open string amplitude as observed in some previous works, which I'm not going to discuss here. But in general, the reason why this is still true, even as a mathematical statement, is still deserve a better understanding. But here, the question that this observation really rises is that how should we interpret this result? How should we think about this part when we really insist that we're using two different signatures? One thing that we can try is that we turn this open string into a corresponding integral representation back into some integration of Cobalt-Nielsen's plus some integrand. And we can try to run the KLT argument of this counter deformation backwards and see if whether we can land on some integration of a closed string wall shape. Then, at least naively, what this fact seems to suggest is that when we consider the closed string correlation functions, in particular when we consider this XX correlations, in ordinary string, this is something proportional to the log of V times V bar. Then due to this flip of the matrix, what it seems to suggest is that instead of doing this, we would like to using something as the log of V over V bar. In a sense, roughly speaking, this is like for the right movers. We are changing the direction of time evolution. And also the boundary conditions. Or maybe an equivalent way to say, maybe an alternative picture is that we are splitting the left movers and right movers, and we choose to use two different tensions for them, which are opposite to each other. This is just some kind of interpretation, but temporarily I'm not trying to say that this is something really physical. This is something that's a tentative proposal, but definitely that needs to be understood better, whether this really makes sense or not. But at least given this interpretation, we can even try to see whether the picture can be consistent. Say, now if we no longer insist on looking at the superstring, to be simple, we can even look at bosonic string and see whether the spectrum that we learn from this interpretation matches the spectrum we learned from looking at the structure of amplitudes. And it turns out, it seems to suggest that the two pictures is consistent. But actually, even for the whether the KLT argument can run through for this new relation is not very clearly understood. However, one more thing.
If you do the bosonic, what do you get?
So for bosonic, it's like this.
You get the tacking or you get gravity on the...
Yeah, exactly. So first of all, you get all the massless states. But apart from them, you see a tachyon. But there's more. You also see a state in the first massive excitation, first level of massive excitation. There are these two states. Sorry, three states for the bosonics. Yeah, this is the general thing that you can observe by trying to play with this game. But apart from the interpretation, what I would like to make the comment that that I would like to make in the end is that given this fact that now we have a truly stringy construction of field theory amplitudes, in particular here we are really using ordinary string amplitudes, perhaps that may provide some intuition of drawing connections between ordinary string theory amplitude and the expression that I have been talking about in the first half of this picture. In particular, because if we now really think in terms of this kind of weird correlation functions and try to run through the Gauss-Mender argument again, so
you're from these high energies, and you want relations that are for all energies, right?
That's true, but here, suppose everything works out nicely, but at least intuitively, in the closed string formula, you get something that looks like this. Of course, there could be issues like whether the whole thing is single valued or not, but at least if there are some certain integral that is turned out to be identical to this, then that means, first of all, the dependence on the other point has to be trivialized, even though it will seemingly have a non-trivial expression. And then perhaps we can, that means the low energy limit and the high energy limit will indeed get identified for this function. And then we just need to move to the higher energy limit and do the computation. And the result will be guaranteed to be identical to the low energy limit, where we expect the field theory. That's just some hand-waving comment, but surely this needs to be made more rigorous. So that's all what I want to say today. Thanks.
Maybe I missed something, but a lot of this construction is based on ansatz for C at the beginning. So is there a sense in which that's supposed to be the unique solution to those consistent conditions?
Oh, it's not a unique solution. It's just something that you can put there which makes the thing consistent. It's not a must that you have to use this thing that I told you.
So are there other known C's that you can run this construction through with?
Sorry?
Are there other known C's that you can
Oh, sure. For example, there's another effective theory, an effective scalar theory, which people usually call the Galilean. This is like something arises from the study of massive gravity. And in general, when people talk about Galilean, it's a whole family of theories parameterized by some couplings there. There's a particular value of the coupling that you can choose that where an accidental extension of the symmetry happens. And for that guy, let me call it a special Galilean. I'll not talk about the details. For this particular theory, this amplitude turns out to have a very, very simple expression. In the integral, you put nothing but the function of A. The A is the small part of that side that I told you before. You put it with a fourth power, and that's it. This is everything. Also, actually, there's a whole web of examples that we have known so far, and basically all of them can be think about as starting from a GR, you can do something that's very natural. You take the amplitude here, and you compactify. You push some of the polarizations into an inner space so that they become some vectors, and so you get some photons coupled with gravitons, and you can even make it more non-trivial so that you no longer have photons, but instead you have gluons, and they interact with gravitons, and you can get a very compact formula for any amplitude of this sort. Also, you can do something more non-trivial to land on the Born-infield theory that I told you before. That's also a closed formula, and you can go even further to land on some other theories. There's a whole web. And actually, there is something that turns out to be not quite familiar arising from this playing. And although we have a collection of theories where we can draw some connection between them, but the physical interpretation of those connections are actually not quite well understood.
So are there prospects for taking this beyond tree amplitude?
There are, and people have been thinking about it for quite a long time, although there hasn't been, there are progress, but so far, none of them seems to be very practical from the usual purpose that we have for the group. But there's a clear proposal for that. So if you take this picture of another line Riemann sphere seriously, actually the way I motivate the equation here, there's an alternative way to motivate the scalar equation, which, since I have time, I can comment a little bit more. So suppose, let's attempt to forget about all the identities relations. Let's insist on that we want to formulate the thing by some sphere, and we want to identify the punctures with the incoming part, with the external particle. And since they are local, we try to associate some data. In other words, the momenta for the corresponding particle for each of these punctures. There are some local things that you can compute. Once you have this object, you can think about some differential form, which is valued in the Lorentz space, and we require that it has simple poles on each of the punctures, and the corresponding residue is the corresponding data that we have. By insisting on this, you get a unique solution, which is the sum of A from over all punctures, and for each of them, you take the corresponding momentum, let it be over sigma minus A d sigma. You can first construct this object, and then what you do is that you construct a quadratic differential form by taking the Lorentz invariant product of two copies of this. And then you impose that this should be identically real everywhere on the Riemann sphere. This is just some proposal. There is actually some motivation for why we impose this, but temporarily let's accept that. By insist on this, you can actually derive the scattering equations again. So this is another way to view how these equations are arise, although it's less physical. Okay, this is at tree level. But then given this picture, you can immediately generalize it to higher loops. Once you insist on this Riemann sphere for tree level, then in analogy with string, you can naturally think about some Riemann sphere of higher genus for the corresponding loop level. And then you again construct some meromorphic form on the corresponding Riemann surface, and then ask for this condition again. Of course, now at loop level, the equation will, in general, depending not only on the locations, but also on the moduli. And the spirit is that the equations should determine them all, although there could be many solutions. And then you do some similar things as constructing a function, evaluating all the solutions, and sum on top. But what people
now you're neuromorphic forms aren't determined just by their puncture. Don't you have some, just because just the space of the vector space of the neuromorphic form grows with the genes in vitro.
Right. Let me see.
So you need some other.
You also have a loop moment.
Yes. So here, what people can directly compute are really, you actually need to feed a specific value of the loop momentum into the equation, and then so as a result, what you get is actually a something that has the potential to be the loop integrand. But then, of course, there's the remaining issue of how to do the loop integration. And actually, if you directly do this, then even at one loop, it's a very complicated system to solve. And even for 4.1 loop, people haven't understand it quite well. They cannot even determine how many solutions are there in general. However, at loop level, you can do some other trick. So in general, you are formulating this by integration with functors, moduli, and you localize them using some equations and do some integrand. This is your story, and this is the loop integrand. This is complicated to solve, but what you can try to do is that you can think about applying some global residue theorem so that you can first localize this moduli on some points. And it turns out that there is a systematic way to push this to the infrared region such that the Riemann surface has this non-separating degeneration. And then the picture emerged from this residue theorem is that for any loop, almost you can always think about this as being obtained by starting with a sphere and then hide a pair of particles one by one in order to create the loop. And when you translate it back into this picture, then this system almost looks like the same as what you have at tree level, and you can do the computation. But there is actually some issues that people have to pay attention for the final result you get, because this kind of formulation at loop level does not directly generate the result that you can naturally expect from a Feynman diagram calculation. So it's not completely clear how they can be identical. There are arguments of why they should produce the same result after performing the loop integration. But actually, to do the loop integration using this result is kind of tricky. And even at one loop, you need to have a better understanding. It's not completely clear at all.
Okay, thank you.